So we are going to use our newly discovered skill of polynomial long division to do some analysis on a rational expression. Now that's a monster function up there. It's a cubic divided by a quadratic. So we're going to have to tease this thing apart using the factoring ability of polynomial long division. And we're also going to have to approximate what this function looks like without all the garbage in between by just flat out doing the division on this particular function. So I'm going to start with that. I'm going to take what it says here, this cubic, and I'm going to divide it by this parabola using the long division algorithm. So I can start off by doing x squared plus 5x plus 6 is dividing x cubed plus 2x squared minus 11x minus 12. So just running through the algorithm, in order to make an x squared and x cubed, I need an extra power of x. So x of these is x cubed, x of these is 5x squared, x of these is 6x's. Take them out of the pile. I'm left with 2 minus 5 is minus 3. Minus 11 minus 6 is minus 17. And minus 12 minus nothing is just minus 12. Alright. And then in order to get a negative 3x squared from this, I need a factor of negative 3. So negative 3 times x squared is negative 3x squared. Negative 3 of these would be negative 15 of these. And negative 3 of those would be negative 18. So if I take those things out of the pile, this is gone. Minus 17 minus minus 15 is minus 2. And minus 12 minus minus 18 is 6. So what I've figured out there is that this function, f of x, could also be written as x minus 3 with a remainder of negative 2 plus 6 that still needs to be divided by this horrendous thing over here. Alright, so I'm just going to leave that up there for a minute. Clear the second thing I'm going to do is to actually factor the numerator, that's the thing on top, and the denominator of this particular rational expression. So I'm going to start with a cubic. So what I'm trying to figure out is, are there any values that would make x cubed plus 2x squared minus 11x minus 12 equal to 0? So just taking a look at that, if I made this negative 1, that would make that positive 11. I'd have 11 and 2 is 13, and minus 1 and minus 12 is 13. So I'm going to try x equals negative 1. So minus 1 cubed plus 2 times minus 1 squared minus 11 times minus 1 minus 12. So minus 1 cubed is just minus 1. Minus 1 squared is 1 times 2 would be 2. Minus 1 times minus 11 is positive 11 and negative 12 here. Those two together are 13. Minus 1 minus 12 is 13. So indeed, that works. So now that I've figured out a value that is a solution, so since x equals negative 1 is a solution, therefore x plus 1 is a factor. So I'm just going to divide that factor out of this cubic so that I can continue splitting the cubic up into little bits. So take my cubic on top, and divide it by this new factor that I'm trying to get rid of. So to make this into an x cubed, I need an x squared. X squared times x is x cubed. X squared times that is 1x squared. And if I take them out of the pile, 2 minus 1 is just one of them. That's still here. That's still here. In order to get an x squared from that, I need a factor of 1x. 1x times x is 1x squared. 1x times 1 is 1x. Take those out of the pile. Minus 11 minus 1 is minus 12x. Minus 12. And I'll need a factor of minus 12 here. Minus 12 times x is minus 12x. Minus 12 times 1 is minus 12, giving us a clean division. So I'd like to just take a minute to clarify what we're doing here. I just did this division and got this answer, and it was not clean. And I should not expect this to be clean, because these functions have, if it were clean and the answer were x minus 3, that's just a line. It's not a rational expression. It needs this piece here in order to make all the exciting features happen. So when you do that straight up division, you shouldn't expect it to be a clean answer. When you do this one, I'm using the same tool, but I'm hunting for a different feature. I'm just trying to factor the top here, and if you remember all of the factoring questions that you did on the back of the worksheet, they all ended up nicely because you cleaned up, like you picked a thing that gave you a clean answer. You made that happen. You found a feature number that made this 0, and then you pulled it out. If this makes that 0, it comes out evenly. So this part should always work out even for you. So what I've got there then is that this cubic on top can be written as this factor times this piece that's left. And of course, there is still something in the denominator here. Alright, now I'm going to get rid of this because we don't need it anymore. Alright, so to finish this then, if I look at this thing here in the bottom, 1 times 6 equals 6, and 1 plus, sorry, 1, no, that's not going to work. 2 times 3 equals 6, and 2 plus 3 equals 5. So I can split this thing. Instead of writing it this way, I could write that. I'm going to do it here. In the bottom as x plus 3, x plus 2. So I just use basic trinomial factoring to split this into its two factors. And if I look at this piece here, plus 4 times negative 3 would give me negative 12, and 4 minus 3 gives me 1. So I can split that trinomial up like this. And this one is still kicking around because we factored it out in the first place. So I've taken the rational function as it was handed to me, and I've done two things to it. I've written it as its end behavior form, and I've written it in its fully factored form. I'm going to get rid of this because I don't need it. So I've provided a bit of structure on the practice problems. So you don't have to do this analysis in this particular order, but it's the order that's been done on the practice problems. So I'm just going to go through them in that order, and then you can figure out what works best for you in the future. So the first thing on there is use factoring to write f of x as a product of linear and rational functions. So I already took this and broke it down into all these little bits. And I'm just going to write them out in order of each type. So my first one, the one that happens at the most negative place, is this guy here. This one has an x-intercept at -4. So I'm going to write that down. Next thing in would happen at -3. So I've got this thing, x plus 3, but do you notice it's in the denominator? So this thing is not like that. It's a rational expression. Next one in would be at -2. So this is also in the denominator. That is also a rational expression. And then I've got this one happening when x is -1. And I have this one happening when x is 3. Alright, so it asked you to write them all out as a sequence of rationals or linear expressions. So we've done that part. Part B is use either the given form or the factored form, or, if you like, the end behavior form, to calculate the y-intercept. So I'm going to choose to use the original form. I want to use this one. Is to get your y-intercept, all you need to do is evaluate the function at 0. And in this particular form, if I put a 0 here, that's gone, that's gone, that's gone, and I'm left with -12 only in the numerator. That's gone and that's gone. It leaves me with 6 in the denominator. And -12 divided by 6 is -2. So there's my y-intercept. Part C, identify the x-intercepts of each piece of your factored composite function. So I'm going to go through all 5 of these pieces, and I'm just going to list the x-intercepts that I would find. So this first one, right, if you forget all the other garbage, if it was just this line will cross the x-axis when x is -4. So there's one x-intercept. This rational expression hasn't been shifted up or down, so it will never cross the x-axis. There's no x-intercept there. No x-intercept here. This one has one at -1. This has one at 3. So the idea here is that because these pieces all have x-intercepts, then the full function that they came from will also have x-intercepts at those 3 places. It's like these are little Lego blocks, right? You take your Lego and you clip them all together, and it does make something more complicated, but when you look at the more complicated thing, you can still see the features of the individual bits. So I've taken this function, broken it up, strung it out as linear or rational pieces, and then identified the x-intercepts provided by those linear pieces. The next step, number D in the analysis, is identify the boundary errors of each of your factored composite function. So if I were to look at that, and I'm after boundary errors, which is just another word for vertical asymptotes. So I'm after vertical asymptotes. This particular Lego block does not have vertical asymptotes. It's just a line. Neither does this one, neither does that one. But this one, this rational expression, this rational function does have a vertical asymptote, and it's been shifted 3 to the left. So this one is going to provide us a vertical asymptote when x equals -3. And this one, this little Lego block, also provides a vertical asymptote, but this one happens when x is -2. So I'm going to have 1, 2, 3 x-intercepts because there are 3 linear pieces, and 1, 2 vertical asymptotes because there are 2 rational pieces. Finishing the paragraph in that section D there, it says, identify the boundary errors of each piece of your factored function. We did that. And which direction the function is headed around each one. So if I have a vertical asymptote, the function can either be coming in like this, or it can be coming in like this. It just depends on which side of the x-axis you're on. So in order to figure that out, I'm just going to guess a number that's close to this, but not quite. So I'm just going to take an extra step of 0.5 in that direction to where x would be negative 3.5. Keep that in your head. X is negative 3.5. Oh, I don't want blue. I want this one. Now, I'm not going to actually do the calculations. I'm just going to hunt for the sign, because all I care about is whether these values are positive or negative. If they're positive, then I zip upwards. If it's negative, I have to be zipping downwards. So if I put this x, negative 3.5, into a bracket where you add 4, minus 3.5 plus 4, it's going to be positive. I don't care the value, I just know it's going to be positive. If I take minus 3.5 and put it into this bracket where I add 3, that's not enough to flip it positive. So this will be negative. Minus 3.5 plus 2, not enough. Minus 3.5 plus 1, not enough. Minus 3.5 minus 3, well, that made it worse, so that's still negative. So if I were to put something just a little bit to the left of this asymptote into my function, I get 2 negative factors which cover each other, 2 negatives which cover each other, and a positive. So negative times negative is a plus. Negative times negative is a plus. A plus times a plus times a plus is positive net when you're done. I don't care how high it is. I don't want the number. I just want the sign. So when I put this negative 3.5 in, I get a net result of positive, which means that this is the asymptote that's going to happen, not that one. So I'm going to try that again, and I'm going to try it on this side of the asymptote. Clear that out. So I need to step this way just a little bit. Instead of going to, well, let's just do a half. So half up from negative 3 would be negative 2.5. Put that here. That's enough to flip it positive. Put that here. It's enough to flip it positive. Put it here. It is not enough to flip it positive, nor will it be here, and that makes it worse. So a negative times a negative is a positive, times a negative is a negative. A negative times a positive is a negative, times a positive is a negative. So net, I mean, there's more negatives. There's an unbalanced negative, I guess is what we're hunting for. So if it's an unbalanced negative, the full result of the function will be negative, so it needs to be this kind of asymptote. It needs to look like that. Right, I'm going to do it on this one as well. So clear everything out here. Well, actually, let's work smart, not hard. If I step half down this way, I'd be at negative 2.5. Well, I already tested negative 2.5 and found that it had a net negative result, so it's got to look like this. If I test on this side, a half up from negative 2 would be negative 1.5. This will be enough to flip it. This will be enough to flip it. This will be enough to flip it, but these two won't be. So I don't have an unbalanced negative there, which is going to give me a net positive result after all these multiplications. So I need an asymptote that looks like this, one that's going positive. All right, good. On to part E. Will any of the features from C and D mask each other? So masking is a funny word. You don't have to use the word mask. You could use the word overlap if you'd like. And the idea here is that you can't have a place on your graph that is both an X-intercept and an asymptote. And if you don't believe me, I'm just going to quick draw one here for you. I'm going to put an X-intercept here, and I'm going to put a vertical asymptote on the same place. And then I want you to imagine trying to connect these two features the way you're supposed to. So here you are, minding your own business, coming along this way, and you see this pink dashed line, and that pink dashed line says fire off to infinity and don't touch this pink line. But you also see a blue dot there that says I'm an X-intercept. You could cross to the other side of the axis if you went through me here. So you go and you try, and maybe we try the intercept. Well, look what you did. You just violated the asymptote, right? You're not supposed to cross that line. So we can't do that. Let's try the other one. I'm going to come along this way, and I'm going to say, I don't like you, X-intercept, and I'm going to follow the asymptote instead. Up you go. But you were supposed to cross the axis here. So that doesn't work either. Like, you violated the rules. So what that question is asking you about masking or overlapping is, do any of these land in the same spot as these? Because if they do, we're going to have to do a little bit more complicated analysis to see which one of them wins, or if neither of them wins. For this particular example, none of these numbers match any of these numbers. So for this particular function, there is no masking because there is no overlap of features so far. Let me get that fake little thing out of the way. On to question F. Use polynomial long division or the limit as x goes to positive or negative infinity to determine the end behavior of this function. Well, in the spirit of working smart and not hard, we just did this right at the beginning. I did that division because I knew I was going to have to anyway. And the interpretation of this particular answer is that this function is basically this line with a bit of other goop thrown in. So this thing here, that's my end behavior. The idea here is that once I get outside of this range, once I get far enough away from the X-intercepts, once I get far enough away from the asymptotes, that this part here vanishes, just sort of drops away. And all I'm left with is this linear chunk. So when I get out to the extreme ends, either to the extreme left or the extreme right, then I start to have a function that looks like x minus 3. So now that I know what it's doing at the edges, and I know where it crosses the x-axis, and I know where it crosses the y-axis, and I know where it has vertical asymptotes, the only thing left to do is to assemble all of these features into a single graph. So let's fetch the grid here, give that a try. I'll do my x-axis in green. Something like this. All right. So first thing I have is a y-intercept at -2. Well, that's here. And I have an x-intercept at -4. That's 1, 2, 3. That's here. And an x-intercept at -1. That's here. And an x-intercept at 3. Well, that's out here. I also have some vertical asymptotes. One is at -3. That's here. And I have one at -2. It's there. All right. And I have this end behavior then that looks like x minus 3. So I'm gonna use the paint to draw this. The line x minus 3 is a normal up 1 over 1 line that has a y-intercept at negative 3. That's here. So I'm just gonna draw that in. My grid is a little hard to see. Alright, so you notice that going through negative 3 there? Now, critically important for your success in this particular topic is you need to remember that that line I just drew is only for things at the end. So,
could we have a custodian lock the front doors now, please?
I'm going to go out to the last feature on the right-hand side of my graph, and I'm going to go to the left-handmost feature on my graph, and I'm going to erase this line between them. Because this line doesn't matter in the middle, it only matters at the ends. So I'm just going to get rid of her there so she's less confusing. Alright. So I know where it crosses the x-axis, I know where it crosses the y-axis, I know where it has to go to infinity, and I know that over here I need to be approximately this line, and over here I need to be approximately this line. So, let's see. I'm going to come in along my x minus 3 line. And the first feature I'm going to cross is this x-intercept. So I'm going to eventually leave my x plus 3 line to cross through here. Kind of missed. Once I'm through, I go up and follow the asymptote. So that's my first segment. In between here, do you see how I'm supposed to ride up this asymptote from below and then go right back down again? Well, if I draw something like that, it would look like that. Now the question is, do I just turn it around here, or do I get to cross the x-axis first? And if I did, if I was able to cross this x-axis, I should have had 2 more x-intercepts, but I didn't. So I have to come from this negative infinity, rise up somewhere, get myself turned back around without crossing the x-axis, and head back down to negative infinity. According to my asymptotes, on this side of this particular asymptote, I'm supposed to be coming from positive infinity, so I'll do that. Coming from positive infinity, I have to go through the x-axis here, through the y-axis here, through the x-axis here, and then once I'm up like that, I have to curl myself back around and get back onto this end behavior line. So there you go. You get this really wonky looking thing, but it has all the features we found. Does it go through the y-axis at negative 2? Yes. Does it have an x-intercept at -4, -1, and 3? -4, -1, and 3? Yes. Does it have a vertical asymptote at -3 and -2? Yes. Does it behave this way appropriately on each side of the function of the asymptote? Yes. As it travels out to extremely high positive or extremely high negative values, does it start to mimic x minus 3? Yes, it does. So that's it. This function, when you sketch it, looks like that. And the way you arrived at it was to take it, use your polynomial long division to get the end behaviors, use your polynomial long division to factor the beast and spread it out into its individual Lego piece parts, and then analyze each one separately. So example 2 here, we have a cubic over top of a cubic. And just like in the last example, I'm going to use polynomial division to put this into its end state behavior, which I had over here, and then to split it up into its fully factored form. So if we do the division one first, I can remember where I keep stashing my markers.
Aggravating.
So I'm going to be taking 2x cubed plus 18x squared plus 40x plus 24, and I'm going to divide it by x cubed minus 2x squared minus 19x plus 20. That's not very tidy. Alright, so to make this into one of these, I need a 2. 2 times x cubed would be 2x cubed minus 4x squared minus 38x's plus 40. Take that out of the pile. This is gone. 18 minus negative 4 would be 22x squared. 40 minus negative 38 would be 78x's. And 24 minus 40 is negative 16. Now I go to continue this algorithm, but now I need to try and turn an x cubed into an x squared. And I can't do that. So I'm done actually after only one iteration of this, and this is the remainder. So this function here can be written as 2 plus 22x squared plus 78x's minus 16 that couldn't be divided by x cubed minus 2x squared minus 19x plus 20. So that's a little funny. We were expecting a line there, we just got a number. But we'll talk about that when we get to the sketching. So I'm going to clean this off, and then we'll have to factor both the top and the bottom. Alright, the first thing I'm going to notice about the numerator is that all of these numbers divide by 2. So I'm going to pull that out, leaving an x cubed, a 9x squared, a 20x, and a 12. And looking at those numbers, they're all added, so the number I'm going to have to guess is going to have to be a negative. And if I made it negative, because otherwise you won't have any subtractions and you'll never get it down to 0. So I'm going to pick negative 1, because it looks like a negative 1 and a negative 20 would be negative 21, and 9 and 12 would be, yeah, let's try that. Try x equals negative 1. So I would have 2 times minus 1 plus 9 times 1 minus 20 plus 12. That's negative 21, that's positive 21. Yep, it works. Okay, so now that I know that that factor works, I'm going to divide it out. So pull out a factor of x plus 1 from this horrendous cubic. So to make this into one of those, I need an x squared. Take it out of the pile. To make this into one of those, I need a plus 8x. Take it out of the pile. And I'll need a 12 here. 12 of those. And it goes in evenly, as we expected. This thing here, that will split as 2 times 6 is 12 and 2 plus 6 is 8. So that's x plus 2, x plus 6. So I can write the numerator of this thing 2 x plus 1, x plus 2, x plus 6. All right, now we need to get the denominator still. Let me clear this off. All right, I'm going to try x equals 1 in the denominator. So I would have 1 minus 2 minus 19 plus 20. 1 and 20 is 21, minus 2 and minus 19 is minus 21, so that worked. So I'm going to be pulling out the factor of x minus 1 from this denominator. So to make this into this, I need an x squared. X cubed minus 1x squared. Minus 2 minus minus 1 is minus 1x squared. And I will need a minus 1 here. Minus 1x times that. Times that is plus 1x. Minus 19 minus 1 is minus 20. And I'll need a minus 20 here. And it goes evenly, as expected. This thing, 4 times 5 is 20, and if I make the 5 negative, this would factor as x plus 4, x minus 5. So my denominator then will be the factor I pulled out, and then x plus 4, and x minus 5. So if I start running through the analysis steps in the order that they're on the practice problems and in the order that the last example was done in, the next thing I'm supposed to do is to split these up as X-intercepts and, as linear pieces and as rational functions so that we can get everything in order. So this thing then, it's got a 2 in front of it. I'll just park that there. The furthest left feature will be this X-intercept. Then the next left will be this one. That's an x plus 4 in the denominator. Then an x plus 2 in the numerator. An x plus 1 in the numerator. An x minus 1 in the denominator. And an x minus 5 in the denominator. Alright, so I should have 1, 2, 3, 4, 5, 6 features to fit onto my graph when I'm done. I go and I do my intercepts next. So the y-intercept will be when at g at 0. So that's gone, that's gone, that's gone. I've got a 24 on top. That's gone, that's gone, that's gone. I have a 20 in the bottom. 24 at a 20, that's 12 at a 10, that's 1.2. Alright. X-intercepts. One will happen when this linear segment hits the x-axis, that'll be at -6. One will happen when this one does. And when this one does. my vertical asymptotes are going to happen here, shifted 4 to the left, so it's at -4. Asymptotes. And then again at x equals 1, and then at x equals -5, or 5, sorry. Alright, we just have to do a little analysis to test which way they're going to be going. So we're going to go with -4.5 here. -4.5 would make that positive. That would be negative, 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 negative. So 1, 2, 3, 4, 5. I have an unbalanced negative, so this one's coming, it's going to head like so. Alright. On this side at -3.5, this one flips positive. These all stay negative. So no unbalanced negatives means it's one of these. At x equals 1, I'm going to slide down to 0.5. So 0.5, 0.5, these are all positive. This is positive. 0.5 minus 1, that's negative. So this one. No unbalanced negatives, so it's one of these. On the other side at 1.5, that will flip this one positive. I have an unbalanced negative now, so it's going to be this flavor of asymptote. If I choose 4.5, so it's just a little to the left of this one, these are all positive except that one, which remains negative, so it's this kind of thing. And at 5.5, this one finally flips positive, so I've got that kind of asymptote. Alright. I'm going to scan through this and check for any masking. And none of these 3 things land on those 3 things. So there's no overlap, no masking. All 3 asymptotes will show up, and all 3 X-intercepts will show up. So all we have to do then is to get this on a graph. So this end behavior up here, if it doesn't have an x, that's just a constant value. So this function, the y values are 2, except in the middle where this garbage gets to do some work. So I'm going to find that on here. 2 is like this. Straight across. What's the g value? Well, it's 2. It doesn't matter where you go. Alright, so I have, since I have pink in my hand, an asymptote at -4. 1, 2, 3, 4. And one at 1. One at 5. 1, 2, 3, 4, 5. And I have a Y-intercept at 1.2, which is there-ish, that'll do. At -6, 2, 3, 4, 5, 6. And at -2. And at -1. And now that I've got all my features on there, I'm going to remind myself that this is an end behavior, not a middle behavior. So I'm going to get rid of this guideline everywhere between the last feature and the first feature. There we go. Okay, so now I'm going to sketch this beast in here. Well, on this side, the left side of this asymptote, I'm supposed to be heading to -infinity. So I just draw that in there, like so. And I'm supposed to be approximating this pink line out on this edge, so I'm going to just draw her in like that then. So we have our first branch. I'm supposed to be descending from this asymptote and ascending on that one, and which is nice because I have some nice dots in the center there. So if I'm doing this from this side, pop through, turn around, come back the other side, and then follow my asymptote back up, like so. Now in this section, I'm supposed to be coming from negative infinity on this side, according to this, and I'm going to negative infinity on this side, like this. And I have to connect them together, but I don't have any X-intercepts, so I can't pop up and cross. I'll have to go like so. And out on this end, I'm supposed to be going to positive infinity on this asymptote. So I'll do that. And then I'm supposed to descend and follow this value without crossing the x-axis again. So there you go. Look at that mess. But if you go through and ask yourself the same questions as we did last time, is this function worth 2 basically everywhere except the mess in the middle? Yep. Does it have 3 vertical asymptotes at those places? It does. Has those 3 X-intercepts? Yes. 1.2 for the Y-intercept. Good to go. And there you have it. Alright, for our third example, we have a quadratic stacked on top of a cubic. So as always in the analysis, I'm going to attempt to run the long division to get the end behavior form. So in this one, I'm going to be taking x cubed. No, I'm taking x squared minus 3x minus 10, and I'm dividing it by x cubed minus 7x squared plus 7x plus 15. So I'm going to try and turn this into one of these, and you can't. Now this happened in the last example, but it happened in the second iteration on the last example. This one happened right at the gate. So the only way for this thing to work is if I take none of them. None of these would be none of these, and then that's my remainder. So this one kind of broke the polynomial long division. You can't divide a lower order power by a higher one. It doesn't work. But we can just write it in that form just for completeness sake. So it looks like the other examples, that this function is essentially 0 plus some garbage that makes some interesting features in the middle. Now, I know that's just 0 plus the whole function, but that's the interpretation of this, is that the end behavior of this, instead of taking off like a line or taking off as a flat value like the last one did, this one has to settle right back down onto the x-axis. That's interesting. So we're going to clean this off, and we're going to have to fully factor the top and fully factor the denominator. So if I look at that denominator, I think of some numbers that might work. If I pick -1, it would flip this to negative. This would be -1, minus 7, minus 14, minus 15. That's going to work. So if -1 works, then the factor I'm dividing out is x plus 1 from x cubed minus 7x squared plus 7x plus 15. So what times this would give me this? I need an x squared. minus 7 minus 1 is minus 8 of them. And around. So we'll need minus 8x of these. Seven minus minus 8 is 15. So I'll need 15 of those. 15x plus 15, which goes in evenly, as expected. All right, now this thing up here, 3 times 5 is 15, and negative 3 minus 5 is negative 8. So this is going to factor as x minus 3, x minus 5. So I'll erase that and then write our factored version. I had an x plus 1, and an x minus 3, and an x minus 5 in the denominator. Now if I look at the top of that, 2 times 5 is 10, and if I make the 5 negative, minus 5 plus 2 is negative 3. So this is going to factor like this. So executing the same procedure that we've been doing for all this analysis, I need to write that as a list of linear and rational expressions, starting with the one that would happen on the leftmost side. So that would be this one, this X-intercept at plus 2, or at negative 2, sorry. And then I have this rational expression, asymptote at negative 1. And then I have this rational expression, asymptote at negative 3. Then I have this X-intercept and this rational expression, both happening when x is 5. I'm a little curious about this example. Alright, but carrying on, to get our Y-intercept, the markers are everywhere now. That would be h evaluated at 0. So this is gone, this is gone, I have minus 10. This is gone, this is gone, this is gone, I have 15 in the bottom. So that's negative 2/3, or negative 0.667, however you prefer to look at that. And for x-intercepts, well, I'll have one at this place when x is negative 2, and I'll have one at this place when x is 5. And then for I will have one at x equals negative 1, and I will have one at x equals 3, and one at x equals 5. So checking the sides of them, if I pick negative 1.5 for the left side of this, negative 1.5 plus 2, well, that will be positive, but all the rest of these will be negative. And negative times a negative times a negative times a negative. They're all balanced, so this is a positive kind of asymptote. On this side, at negative 0.5, this one flips, the rest do not. So it's unbalanced, so it's a negative type 1. A little shy of this would be 2.5. 2.5 would still be negative on this one, and negative on all the rest of them, so it's a downward one. And 3.5 would flip this one positive, balancing my negatives, so it's a positive type asymptote. And then at 5, or 4.5, sorry, a little bit on this side, these would remain negative, so they're balanced, so it's this type. And at 5.5, it finally flips them all positive. So it's one like that. Now that's unusual. We haven't seen one that did that yet. Lots of fun things in this example. Okay, good. End behavior, we already got that. That's this thing here. Okay. Now we need to talk about this masking thing. So if I look, are any of the X-intercepts falling on the asymptotes? And I do see that that happens here. That this function, as it's written there, has both an X-intercept and a vertical asymptote when x equals 5. So if I were to actually plug that in to the equation, and you don't have to do this, I'm just trying to illustrate a point. If I take h and I evaluate it at 5, I'm going to get 5 squared minus 3 times 5 minus 10 over 125 minus 7 times 25 plus 7 times 5 plus 15 5 squared is 25, 3 times 5 is 15, and 25 minus 15 minus 10 is 0. 7 times 25 is 175. 7 times 5 is 35. I said that was 175, 35. 125 plus 35 would be 160, plus 15 would be 175, minus 175 would be 0. So I get this, which you should recognize as an indeterminate form. And anytime you get an indeterminate form, you have to take a limit, because I don't know what this is actually worth. When we get to more exotic functions, like when you start making composites with sines and cosines and exponentials, and you blend all the functions together, we have to figure out who wins, right? Which is more powerful, the top trying to go to 0 or the bottom trying to go to 0? So we always resolve these using limits before, so that's what we're going to do to see if either the X-intercept wins, that's if the top is more 0, or if the asymptote wins, that's if the bottom is more 0, or if neither of them win, if it gets cancelled out in the wash somehow. So I'm going to try taking the limit as x goes to 5 of x squared minus 3x minus 10 over x cubed minus 7x squared plus 7x plus 15. Now, way back in the limits unit, you were given 3 options to try and resolve limits. Number 1 was just plunk the number in, like we did here, and see what happens. Boom, failed. Okay, tactic number 2 was try some factoring first. So, well, there it is. I have it in factored form, and I noticed that in factored form that this piece would divide this piece away. So this should be equal to the limit as x goes to 5 of x plus 2 over x plus 1 x minus 3. Well, just try putting the number in. 5 plus 2 is 7. 5 plus 1 is 6. 5 minus 3 is 2. So I end up with 7 over 12, which is some heinous decimal point, just a little bit higher than half. 0.583. So when I went to do this, if the intercept had 1, this value would be 0, right? A y value of 0 is an intercept. If the asymptote had 1, then this would have fired off to infinity, which it obviously did not do. So net, what seems to have appeared in this rational expression is that the x-intercept at 5 and the vertical asymptote at 5 managed to unwrap each other and leave just a dot somewhere on the grid. So that dot happened when x was 5, right? That's where I was checking, at a y value of 0.583. All right, now we'll talk about exactly what that looks like on the graph when I get sketching it. For now, I'm going to clean this off a little bit and acknowledge that masking made this happen. Okay, good. Alright, so going through the list of features, I have x-intercepts at -2, and I should have one at 5, but these features ended up being masked. So I'm not going to draw them on there. I have the y-intercept at -0.667, it's about here. And I have a vertical asymptote at -1. And I have a vertical asymptote at 3. And then this one was masked. And then I have this weird little feature here. 5.0583. Now, you remember we put the limits in, and you remember when I put a 5 into the function, I got an error. So this little spot doesn't actually exist. So what it looks like on your graph is a hole punched through the grid. So I'm going to draw that in there. At 5, 1, 2, 3, 4, 5, and 0.583, that's about here. There's just a little hole. So the graph can't exist at that point, but it can exist as close to that point as you'd like. So we're just going to draw a little gap there to show that that happened. And my end behaviors, this thing is settling on 0. So 0 is right about here. And I'm going to keep in mind that I'm only drawing it at the ends, not in the center. So the only thing left to do then is to connect all these lines. So this asymptote at -1 is supposed to have a positive climber on this side. I'm going to draw her in. And a negative climber on the other. I'm going to draw that in. This one is supposed to have a negative climber on this one. And a positive on this side. So I have that drawn in there. Well, I've got to get from this asymptote through this intercept, so no problem. But then once I'm through it, I have to turn and get back to my x-axis somehow. I've got a feature like that. In between, I have to rise up, pass through this y-intercept, but I am not allowed to cross the x-axis. I don't have any more x-intercepts, so I'll have to turn her around, send it back down. Now it's all connected. And from up here, down we go. I'm going to get as close to that hole as I can without actually going through it, and then I have to turn and follow the x-axis. So something like that. So I have this graph that ends up with the two vertical asymptotes I expected, and I end up with an x-intercept at the place I wanted and a y-intercept where I wanted it. And then I noted that my masking, right, these two pieces, the x-intercept and the asymptote that might have been, end up canceling each other out at this tiny hole. And that this function, as you go out further, just becomes worth nothing.